Bismillahirrahmanirrahim. Here we show that limit x approaches to c f of x g of x is equal to 0. We are given that limit x approaches to c f of g of x is 0 and f of x is any bounded function. Now start the solution. Given that f of x mod is less or equal to capital M for all x belongs to R and limit x approaches to c g of x is equal to 0. By definition of limit, this implies that for any epsilon greater than 0, there exists a delta greater than 0 such that g of x minus 0 mod is less than epsilon over m x minus c mod is less than delta. Now consider f of x multiplied by g of x minus 0 mod is equal to f of x multiplied by g of x mod is equal to f of x mod g of x mod. As we know that AB absolute value is equal to A absolute value multiplied by B absolute value. F of x mod is less or equal to M. Then this expression can be written as less or equal to capital M into g of x minus 0 mod, and g of x minus 0 is equal to g of x, but here g of x minus 0 is less or equal to epsilon over m, less than epsilon over m. Therefore this expression becomes m into epsilon over m for all x minus c mod is less than delta. M is cancelled out by m in the denominator and we have epsilon. So we have shown that f of x g of x minus 0 mod is less than epsilon for all x minus c mod is less than delta. Therefore we can write this implies that limit x approaches to c f of x g of x equal to 0. By definition we have shown that limit x approaches to c f of x g of x is equal to 0 as required. Question number 2. Given that f is a function from R to R is continuous on capital R and f of c is equal to 8. F of c is equal to 8 for any c belongs to R, then f of x is greater than 7 for uncountably many x belongs to R. Solution: since given that f is a function from R to R is continuous on R, this implies that f of x is continuous at every point of R since C belongs to R and f of C is equal to 8. Since C is a real number and f is continuous at every point of R and C is also a real number, therefore f of x is also continuous at C. This implies that f of x is continuous at x is equal to C. By definition of continuity, this implies that for any epsilon greater than 0, there exists a delta greater than 0 such that f of x minus f of c mod is less than epsilon for all x minus c mod is less than delta. Since given that f of c is equal to 8, so we can write f of x minus 8 f of x minus 8 mod is less than epsilon for all x minus c mod is less than delta. Take epsilon is less than 1. This implies that f of x minus 8 mod is less than 1 for all x minus c mod is less than delta. This implies that minus 1 is less than f of x minus 8 is less than 1 for all minus delta is less than x minus c is less than plus delta. This implies that 8 minus 1 is less than f of x is less than 8 plus 1 for all x minus delta is less than c minus delta is less than x is less than c plus delta. This implies that 7 is less than f of x is less than 9 for all x belongs to c minus delta comma c plus delta. This implies that f of x is greater than 7 for all x belongs to c minus delta comma c plus delta. Since we know that every interval either open or closed contains uncountably uncountable real numbers, therefore we can say that f of x is greater than 7 for uncountably many x belongs to R as required. Question number 3. If f is a function from R to R is continuous on R and f of R is equal to 0 for all r belongs to q, then f of x is equal to 0 for all x belongs to R. Now start the solution. Let x belongs to R. Q is dense in R. This implies that Q clear is equal to R. If x does not belongs to Q, then x belongs to Q derived. This implies that there exists a sequence xn in Q such that xn approaches to x. Since f is continuous on R, so this implies that f of xn approaches to f of x as n approaches to infinity. This implies that f of xn minus f of x mod approaches to 0 as n approaches to infinity. Since f of x mod is greater or equal to 0 is equal to f of x minus f of xn plus f of xn mod is less or equal to f of x minus f of xn mod plus f of xn mod. Since all elements of the sequence belongs to Q and f is identically 0 at every point of Q, therefore f of xn is equal to 0, and f of xn approaches to f of x, therefore f of x minus f of xn is also approaches to 0. So this expression approaches to 0 as n approaches to infinity. So we have 0 is less or equal to f of x mod is less or equal to 0. This implies that f of x mod equal to 0. This implies that f of x is equal to 0. Since x is arbitrary real number, this implies that f of x equal to 0 for all x belongs to R as required.